Hello friends, in our last video we discussed about photoelectric effect. So let's discuss one very easy example of photoelectric effect. Suppose a question is given which says when a photon of 18 electron volt is irradiated on a metal, the kinetic energy of the ejected electron is 4 electron volt. What will be the kinetic energy when the same metal is irradiated with 12 electron volt photon. Okay, so this is the question. When a photon of 18 electron volt is irradiated on a metal, the kinetic energy of the ejected electron is 4 electron volt. What will be the kinetic energy when the same metal is irradiated with 12 electron volt photon? We know that from photoelectric effect, h nu, this is the energy of the photon, equals h nu naught. This is the work function of the metal, or the threshold energy which we discussed. It is also known as the work function, plus kinetic energy. Okay, so we can also write it as h nu equals W plus kinetic energy. Work function is represented with W. So from here, if we substitute the values, we get 18 equals W plus 4 electron volt. Fine. So from here, we get W equals 4 electron volt. Or no, the W equals 14 electron volt. Okay. Now, if the same metal is irradiated with 12 electron volt photon, if the 12 electron volt photon is irradiated, then as we can see, it does not exceed the work function of the metal or the threshold energy of the metal. Therefore, with 12 electron volt photon, no ejection of electron will take place. So we can write here that therefore no ejection of electron will take place with 12 electron volt photon. Okay, so there will be no kinetic energy of the ejected electron, as there is no ejected electron. Right. So now let's go further in our chapter. Now, one common example, one common feature that we have seen in our life at some point or the other, that whenever a white light, suppose this is a white light, is irradiated and passed through a prism, it splits into a band of 7 colors. Okay, if this is the screen, then we are able to see 7 colors on this screen. So here we see violet, then indigo, then blue, then yellow, then orange, first we see violet, indigo, blue, then green, then yellow, then green, then orange, then red. Okay, whenever a white light is passed through a prism, whenever a white light is passed through a prism, we all have seen that it splits into a band of 7 colors. If this is the screen, suppose, then we see here a band of 7 colors. The colors are violet, indigo, blue, green, yellow, orange and red. Okay, we also call it as Vibgyor. So here this portion has got the maximum wavelength, and because of this reason it bends very little, and this portion has got the minimum wavelength. Because of this it bends very much. So this portion has got maximum wavelength in this band, maximum lambda and minimum lambda. It has maximum lambda in this band and it has minimum lambda. So wavelength increases in this manner. Okay, so here this band of different colors is called as spectrum, or by definition we can also say that a series of electromagnetic waves with different wavelengths is called as a spectrum. So series of electromagnetic waves with different wavelengths is called as spectrum. Okay. Now this particular example, this whole example is continuous spectrum, as the colors that we all see here is continuous. That is, you will not see any separation between two different colors. Okay. So this is continuous spectrum. This is an example of continuous spectrum. Okay, this is an example of continuous spectrum, and we are able to see it only because it falls in visible region. Okay, so whatever falls in visible region we are able to see it. We are not able to see the ultraviolet rays of sunlight because it falls in ultraviolet region of of electromagnetic spectrum. Okay, so now let's see how many types of spectrums are there. We are going to study very briefly about emission spectrum, about absorption spectrum and about line spectrum. As the name suggests, that an emission spectrum must be related with the emission of any radiation, or the absorption spectrum must be related with the absorption of a radiation, and that is true. Well, I'm going to discuss the mechanism of emission spectrum and absorption spectrum in a little detail, so that you all get a good idea of what an emission or an absorption spectrum is. Okay, well, there are different energy levels of an electron. Okay, there are different energy levels. Suppose this is level 1, this is level 2, and suppose here this is level 3. Fine. So this gap is known as, the gap between the energy levels is known as the energy gap. This is the energy gap, and the energy, that is delta E, is E2 minus E1. Okay, suppose the energy of this is E1, this energy of this level is E2, energy of this level is E3. So this energy gap delta E is E2 minus E1. Okay, so now suppose we irradiate a sample, or suppose an electron is sitting here in the energy level 1. Suppose an electron is here. Now, if we irradiate this electron with energy as delta E, remember the energy has to be delta E, or if this is delta E1 and if this is delta E2, if this is delta E2, then if we irradiate the energy and this electron with delta E1 or delta E1 plus delta E2, then depending on the value of this energy of this photon, if this photon h nu is delta E1 or delta E1 plus delta E2, then depending on its value, the electron will make a jump from this level to this level, to the level E2 or to level E3. Okay? So the wavelength, we measure the wavelength of the photon, of the incident photon, and the wavelength at which the electron has made the jump. So to study the absorption spectrum, the continuous spectrum is irradiated on an electron. Okay? In case of absorption spectrum, now this electron is irradiated. Electron is irradiated with a continuous spectrum of radiation. Okay. Now let the continuous spectrum of radiation contains. So if we say let, it contains wavelengths as lambda 1, lambda 2, lambda 3, lambda 4, and so on. Okay. Now what will happen? The electron, this electron will absorb the wavelength corresponding to this energy, or the sum of these two energies only. It will not absorb any other wavelength. Okay. Because the electron can make the jump from one energy level to any other energy level only. It cannot make a jump from this energy level to in between. Okay, to in between any two energy levels. So therefore electron will absorb only wavelengths with value as delta E1 or with value as Hc upon delta E1 or Hc upon delta E1 plus delta E2. Now how have we got it? Well, this is very easy. We know H nu equals Hc upon lambda equals delta E1. So from here lambda is Hc upon delta E1. Okay, so it will absorb only wavelengths with value this or this. Now if it absorbs the value this, then that wavelength will be missing from the continuous spectrum. From the group of values, these two values will be missing. Okay, so therefore suppose if only three levels are there, and the very first energy level is known as the ground state of an electron. The state in which the electron is most stable is known as the ground state of an electron. Okay, this is the ground state. Okay, and in this case, in this particular case, electron will make the two wavelengths missing from the incident radiation. Okay. Now from the quality of the wavelengths that are missing, a band is generated or a spectrum is generated. Okay. Those spectrums are known as absorption spectrum. So this spectrum is called absorption spectrum. Okay. This particular spectrum is known as absorption spectrum. Now, another type of spectrum is emission spectrum. Okay, so now this is the ground state, and this energy level is first excited state. Now suppose the electron is at this level. The electron is in the first excited state level. Now it cannot stay in this level because it is unstable. The electron is stable only in its ground state. It is not stable in the first excited state or any other excited state. So it will tend to come back to its ground state level. Okay. So when the electron comes back to the ground state level, it releases the energy. Whenever any electron it comes back, so it will release the energy because now the energy is getting decreased. This electron has got higher energy than it would have been when it was at if it is at the ground state. So therefore, while coming from first excited state or any other excited state to ground state level, it will release energy. Okay. So emission spectrum is very easy to visualize. Emission spectrum. Whenever, if the definition is written, then the definition will be like this. Whenever an electron falls from an excited state to ground state, it releases the energy and hence emits a radiation of a particular wavelength. Okay. So therefore, and since the energy gap is delta E1, so therefore the wavelength released is wavelength of emitted radiation. Lambda is hc upon delta, or lambda equals hc upon delta E1 plus delta E2, depending on which energy state the electron is excited to. Okay. So therefore the wavelength of emitted radiation is, so now the study of these wavelength is known as emission spectrum, because now we have got the spectrum from the emission of radiation by an electron. Okay. So suppose if I heat a metal rod, or in case of flame tests of calcium or magnesium, if you heat the element, it will absorb some energy, and hence it will move to the first excited state, okay, or any other excited state. Now when it comes down or when it comes back to the ground state, it emits the radiation which falls in different region of visible spectrum. And because of this, depending on the color, you infer that this particular type of element exists in this given compound. Okay, so therefore the study of this emission spectrum is known as emission spectroscopy. So the study of spectrum is called as spectroscopy. Okay. Now this spectroscopy is further divided into different classes, because it is further divided into different classes depending on the type of spectrum which you are studying. For example, in case of H2 molecule, if you study the vibration of different atoms, then we call it as vibrational spectroscopy. Or the rotation of the two atoms, then we call it as rotational spectroscopy. And similarly, it is the further classification is done based on the type of the spectrum which you are studying. Okay, so another type of spectrum is line spectroscopy. For example, when an electron is fallen from the excited state to ground state, depending on different excited states, it will emit different types of radiation or different wavelengths of radiation. So it will be observed that the types of radiation that is falling will give you an impression of lines. Okay, it gives you an impression of lines, and hence the study of those type of spectrum is called as line spectroscopy. Okay, or the spectrum is known as the line spectrum. Well, remember that a spectrum of any element is unique. Spectrum of any element is unique. No two element, it means that no two element will have the same spectrum, and therefore by studying the spectrums in different types of spectroscopy, you can make out which element exists in the given which element exists in the given subject of study. Okay, so you can make an analogy with the human fingerprint. Every human being has got different fingerprint, and hence we can say that spectrum of any element is the fingerprint of that element. Okay, so in case of line spectrum of hydrogen, and whenever an electric discharge is passed through the hydrogen molecules, we see, in case of hydrogen atom, we see a line spectrum. Okay, so if an electric discharge is passed through hydrogen, we see line spectrum, the wavelength of which is the wavelength of the line spectrum. In case of line spectrum of H2 molecules, you see the wavelength, or 1 upon lambda, equals some constant. I'll write it as K or R. Let's write it as R because it is known as Rydberg's constant. 1 upon n1 square minus 1 upon n2 square. We are going to see later that energy is inversely proportional to n square, or being more precise, for hydrogen-like molecules, we are going to discuss what is an hydrogen-like molecules. Energy is directly proportional to the ratio of Z square upon n square. Z is the atomic number. Okay, so this here 1 upon lambda, or it is also known as the wave number, it equals 109677 1 upon n1 square minus 1 upon n2 square. So the depending on the value of n1 and n2, it falls in different region of electromagnetic spectrum. For example, if n2 equals 2, if the spectrum falls in visible region, so that is the only spectrum which we can see with our naked eye. Here this is n1. If n1 is 2, then the spectrum falls in visible region. Well, here n1 and n2 are, this is the initial energy level. We discussed that the electrons has different energy levels. Okay, so this is the initial energy level. This is the final energy level. Okay, so here different value of n1 will give different series of spectrum. It is based, the series are named after their particular discoverers, after their respective discoverers. So for example, the series n1 is known as Lyman series. N1, whenever n1 equals to 1, it is Lyman series. N2 equals 2 gives us Balmer series. N3 equals 3, it gives us Paschen series. And so on, and here all are n1, sorry for this mistake, and n1 equals 4, it gives us bracket series. Okay, so different values of n1 gives us different values of, or gives us different series which are named after their respective discoverers. So the line spectrum of hydrogen molecules, the wavelength, in case of line spectrum, the wavelength is given by this equation. Okay, so for example, if you are asked that the first line of Balmer series, now the first line of Balmer series means n1 equals to 2 and n2 equals 3. Okay, so in the wavelength of first line of Balmer series you can easily calculate. If you put 1 upon lambda equals this into 1 upon 2 square minus 1 upon 3 square. So after solving it and then taking the reciprocal, you will get the value of lambda. And once you get the value of lambda, you get the value of energy very easily. So from here we can also calculate from this expression what is the energy gap, what is the value of energy gap between two energy levels. So let's see what is the energy gap between two energy levels. From here you can easily get it. If you multiply both sides by Hc, so here Hc upon lambda equals Hc, both are constant, into 109677 into 1 upon n1 square minus 1 upon n2 square. So these n1 and n2 are the energy gaps. This is n1, n2, n3. Okay? These are the energy gaps between subsequent levels. So this is the energy gap between these two levels. This is the energy gap between these two levels, and this complete gap from this point to this point is the energy gap between n1 and n3. So therefore from here we can say that energy gap, that is delta E, equals H into C into 109677 into 1 upon n1 square minus 1 upon n2 square. We are shortly in our next video or so we are going to arrive at this conclusion. We are going to see the proof of this particular expression of energy gap. Okay, so remember that only Balmer series, in which n1 equals to 2, falls in the visible region, if n1 equals 1, it is the Lyman series. For n1 equals 2, it is Balmer series. For n1 equals 3, it is Bastian, and then Brackett, and then Humphrey, then Pfund. There are many series as proposed by different scientists at different times. Okay, so this was all about the spectrum, about the electromagnetic spectrum and emission and absorption spectrum. Now here one extra knowledge which I would like to pass on. If you are not interested, the upcoming part of this video you can skip it. So because this particular thing is not included in the syllabus, what I am going to teach right now is not in the syllabus of IIT JEE, but still about a little bit extra knowledge about absorption and emission I am going to discuss right now. So you can very well skip this portion, or you can skip this video, because this is going to be the last discussion of this particular video. So after some time, after some videos, we are going to see that electrons have different spins. Electrons have different spins. Okay, so spins S, it is denoted by S. It is either half or minus half. This is denoted by up arrow, and this is denoted by down arrow. Okay, an electron in one orbital, we are going to see it later what an orbital is. An electron in an orbital is always paired. By paired, it means they have opposite spins. Opposite spins minimizes the repulsion between the electrons, and hence they can stay in one orbital. Okay, whereas two electrons in different orbitals are not paired. It means they have same spins. Okay. Now in this case, since they have opposite spins, so therefore capital S is the sum of both the sum of the spins of both of the electrons. This is 0, whereas in this case capital S is 1. In this case it is plus half minus half, it is 0. It is plus half, it is 1. So therefore the value of 2s plus 1 in this case is 1, and in this case it is 3. Okay, so this is known as singlet. This is known as triplet. We are not going to discuss in detail what singlet or triplet is. This is not there in the syllabus. And this 2s plus 1 equals, why do we calculate 2s plus 1 also, we are not going to discuss it. Okay, so this is known as singlet, this is known as triplet. Fine. So now these singlet and these triplet character of electrons have different energy levels. Suppose this is S0, it means singlet ground state. This is first excited state of singlet. We have discussed what excited state is. This is second excited state of singlet. This is S2. Okay. Now there is nothing like ground state of triplet. Okay. Always there is first excited state of triplet, then second excited state of triplet. Triplet has no ground state. In the ground state, electrons are always in singlet state, so that they are the most stable species. Okay. So here, if an electron is here at E, at S0, and if some energy is given, H nu. Suppose the energy is sufficient, or the energy is equal to delta E1 plus delta E2, then electron will shift here, S2. Okay, it will make a jump from S0 to S2. I have made this arrow actually wrong. It is always denoted by vertical line, because the arrow is always denoted by vertical line because the energy gap between the two levels is directly proportional to the separation, or is directly proportional to vertical separation between two levels. Okay, so therefore this is always denoted with vertical lines. So if this electron makes a jump from this level to S2 level, suppose, now in order to come to the ground state, this electron has two choices, either to go here or to come S1. Remember, always the electron from S2 can never come directly to S0. Okay? It will first come to S1 and then it will come to S0. Okay? So, now if the electron has jumped from S2 to T2, then again it has two choices, either to go from T2 to S1 or to come from T2 to T1. Fine. Now from here T1 to it will come to S0. Okay? It will come to S0. So, if the electron, you must have heard about fluorescence and phosphorescence, that this particular compound shows fluorescence, this is fluorescent light. Okay? You must have heard a lot about fluorescent lights because you see it in your homes. These are the compact fluorescence lights which you all must have seen, but have you ever wondered what those lights are? Actually, when an electron comes from S1 to S0, we see fluorescence. This process is known as fluorescence. Whenever an electron comes from T1 to S0, this is known as phosphorescence. Okay? This is fluorescence and this is phosphorescence. So these are the two processes depending on the type of transition electron is going through. If it is coming from S1 to S0 and if it is coming from T1 to T0. Now, the radiative emission, this is known as radiative emission because this shows, this is backed by the evidence of observation. It means that you can see fluorescence or you can see phosphorescence if it falls in visible region. But you cannot see this. This is known as non-radiative transition. This is known as non-radiative transition. If an electron comes from S2 to S1 or S2 to T2 or T2 to S1 or T2 to T1, these all are non-radiative transitions. Non-radiative because it does not radiate anything. Non-radiative transitions. By transition, since we know by transition it means change, to change. So therefore an electron is going through some change in its state throughout the process. So this is known as non-radiative transition. This is known as the radiative transition. The radiative transition. Okay? Because it radiates something which you observe. Now the purpose of discussing all this is to make you familiar in a more comprehensive manner about the emission and absorption. Now in this process here, absorption is taking place. Absorption of radiation is taking place. Okay? A particular wavelength is absorbed by this electron and it has moved to S2 level. Now here the emission is taking place. Okay, from this point to this point or from this point to this point, emission is taking place. And since this emission is recorded, it is marked by different wavelengths depending on this energy gap. Okay, this emission depends on the energy gap between these two states. And since it involves some energy, therefore there must be some wavelength. And recording those wavelength or frequency, we study the behavior of this electron and hence we identify the elements which are present in our sample. So I hope this is clear to you. You have understood something from this discussion, but if this discussion is not clear, then you do not need to know about it. Just don't give any stress to your brain by thinking about this if you do not understand it. So this is fluorescence, this is phosphorescence. Okay. So that's all for this video. See you in the next video. We are going to discuss about Bohr model in our next video.